Welcome. This is a video series to look at the proof of the mean value theorem. This is part 3 in the series and the final part of the series. The first installment of the series looked at Fermat's theorem for the derivative at extreme values. The second looked at Rolle's theorem, which looks at turning points of functions. And now we're going to use those two theorems to allow us to prove the mean value theorem. The mean value theorem is a theorem that starts again with a function. We're looking at any function that's defined to include a closed interval from a to b in its domain. And our hypothesis, the requirements for our function, first, our function needs to be continuous on the closed interval. This means it's continuous at every point inside the interval, and the limits reach endpoints that the function has. So you can't have vertical asymptotes or other limits without values at the edges. And secondly, the function needs to be differentiable on the interval of the interior, so every point in between. That's all it takes. And the theorem concludes that if you know a function is continuous on the closed interval and differentiable on the open interval, then there exists some value c between a and b, so c in the interval from a to b, where the slope at c, f prime of c, this is the instantaneous rate, is equal to the average rate of change over the entire interval. So this is the slope between the ends. The proof is fairly straightforward. It relies on the idea of constructing a function for which Rolle's theorem will apply. And then Rolle's theorem will do all the heavy lifting. All right, I have a function f of x, and I know that there's this average rate of change, and so I'm going to define a new function. So let's call this our h function. And it's going to be defined as my function f of x minus this average rate of change slope, f of b minus f of a over b minus a, multiplied by x minus a. Well, how does this work? H evaluated at a will be f of a minus this slope, the average rate of change, f of b minus f of a over b minus a, times a minus a. That's 0. And so the second term goes away, and I get h of a is the same as f of a. H of b, what's that? H of b is f evaluated at b minus this slope, f of b minus f of a over b minus a, times x, which is b minus a. And this time, the denominator cancels b minus a, and I get f of b minus f of b minus minus, so that's plus f of a. Okay, we have a function that at the edges, at a and b, both sides are equal to f of a. Because f of x is continuous, and we're just subtracting a linear function, we know that h of x is continuous, and h of x is differentiable because f of x is differentiable. In fact, I can calculate h prime. It's equal to f prime of x minus this average rate of change, f of b minus f of a over b minus a, times the derivative of x minus a, that's 1. So this actually is the formula for h prime of x. My h of x meets all the requirements for Rolle's theorem. It's continuous, the same place as f is continuous. It's differentiable, where f of x is differentiable. And the left value and the right value on the interval have the same value. So Rolle's theorem guarantees that h prime at some point equals 0 for some c. So when I put this c into my formula, h prime of c, that's equal to f prime of c minus the slope, the average rate of change. That has to equal 0. And the only way that's equal 0 is if f prime of c equals this average rate of change. And that's the conclusion of the mean value theorem. There's a picture that's often associated with the mean value theorem. So let's draw that typical picture. I've got a function, I've got my endpoints, and we're saying that you have a function that joins these. If I calculate the average rate of change, this is my average rate of change, and try to draw any function that's continuous and differentiable, assume that I didn't draw any vertical spots there. What's happening is the mean value theorem guarantees that there's some point where the instantaneous rate, f prime at this point, equals that average rate of change. The tangent line is parallel to the secant line. Now that we've proved the mean value theorem, how does it get used in practice? The key idea of the mean value theorem is that there's this connection between the average behavior of a function on an interval, so that's the two separated points, is related to the value of a derivative at a single point. And this allows me to understand how much a function can change over intervals. The most common application is in terms of where the derivative is positive and negative. So if I know that the derivative is always positive, then when I look at the average rate of change always has to be positive, and that means the function is increasing. Similarly, if the derivative at every point is negative on an interval, that's how I guarantee that my function is decreasing on an interval. And then, this is related to antiderivatives. If I discover that the derivative equals 0 at all points, then that actually guarantees that the function must be constant on the interval. And so I'm going to use the first two, where the derivative is positive and negative. I'm allowed to now use sign analysis to decide where a function's increasing and decreasing. And finding out where the derivative equals 0 allows me to come up with this connection to antiderivatives. If I have two different functions, f and g, that have the same derivative, so f prime, big F prime, and big G prime both equal the same function for every x in an interval. And it's important that this is an interval. We don't just jump over a discontinuity or something. The mean value theorem guarantees that the difference between the functions is constant. And so that gives me this idea that antiderivatives can only be different by a constant. So if I have two functions that are antiderivatives to the same function, then f of x must be g of x plus a constant for some constant c.